Hello, everyone. Thank you for joining for this webinar. So I see several people in the room attending. Today we're going to thermal model validation. So I'm going to start with a short introduction of myself. So I'm Florian Sanchez. I'm product manager at Maya HTT in the product management team since 5 years now. And before that, I worked as a thermal engineer in multidisciplinary teams. So work with system engineer, 3D engineer in MDO for aircraft. So around 15 years of modeling and simulation experience. And today, so I'm going to speak about thermal model validation in the aerospace context. So before jumping into this, the topic, for the ones who does not know Maya HTT is really in the middle of 3 pillars in the innovation and digital transformation. So we do develop software for thermal, structural, AI as well. We are kind of the experts in services for industrial AI and IoT as well. And we are a partner with Siemens, for example, that where we have our thermal solver that I'm going to speak about today. So in summary, we have 40 years of experience in the simulation landscape. So today's flight plan. So I will start with a short introduction about the context. Why do we need to validate our thermal models? Secondly, I will go through our adjoint-based approach, so the tool that we developed over the last year to perform efficient thermal model validation. And then I will use a case study around hydrogen-powered UAV to illustrate how you can accelerate and be more efficient when you would like to validate your model, and especially with certification and industry standards constraints. And at the end, I will conclude and we will give you some key takeaways. So for the introduction, so before anything else and jumping into the topic, I would like to ask you that question. So here you can see a picture of 2 water jets going over like an aircraft. So what's happening there on the runway? Are they cleaning the airplane? Are they celebrating the pilot's birthday? Are they celebrating a new airplane? Or are they cooling the airplane? So I will give you several seconds to come up with the best answer you would think of that image, and we will see the results. Okay, so let's look at the results now. So as I can see, best answer from the audience is that they are cooling the airplane. Really, second one is that they are celebrating the new airplane. So let's look at what is the actual answer. So the actual answer is that they are celebrating a new airplane. That's a common practice industry. But what I liked in our audience today is that you basically selected cooling the airplane. And actually, that's not the actual answer, but could be in the future. Because if we combine climate change and novel aircraft technologies, such as hybrid electric or electric aircraft, which is really sensitive to thermal, we might end up with really critical thermal conditions. And that's something I wanted to highlight, so that a good understanding of the thermal aspects is really important to design an aircraft, but as well for spacecraft, for example. So any new technology involve a lot of thermal challenges, and that's the topic of today. So about the aircraft design process. So let's look at when we perform design, validation, and certification. So you can see here on that slide that you have the several stages of the aircraft design process, from the concepts to the architecture definition, validation, and certification. You can see as a line that represents the thermal analysis activity or the engineering workload. So usually, thermal analysis, it's something that starts a bit after the other discipline. It's more like an afterthought, and that's happened around the aircraft architecture. Currently, with all the trend in the simulation software industry, you might have heard about the shift left approach, which consists of starting, simulating, doing some design analysis earlier, more or less in the conceptual design phase of an aircraft or a spacecraft, for example, to reduce the engineering load during the architecture or system architecture definition. So the topic of today's presentation is really how we can even reduce more the engineering workload at the validation stage. Because if we start earlier, we're gonna need maybe new type of models. It means that more models to validate and to certify at the end of the aircraft design process. So in summary, an efficient design process requires validating thermal models faster than before. So how do we validate thermal model in the aircraft industry or in the aerospace industry? So a thermal engineer can receive several types of reference data to validate the thermal model. So you can have like data from test campaigns, which can be flight or in-orbit data for space, for example, or ground test campaign, which could be thermal vacuum chamber, thermal balance test. And this can be done for the entire sub part of an aircraft or a specific system or payload of the vehicle. Then you can have reference data that can come from high fidelity simulations, such as CFD simulation for complex ventilated aircraft base, or external flows for the aerodynamic aspects. And at the end, as well, we can leverage the industry standards or in-house standard to come up with requirements that can be used to validate a thermal model or a design. So in summary, thermal model validation are performed using different sources of reference data. So now let's ask you the question about what type of reference data do you use to validate or calibrate your simulation model. So you should see the poll right now, and I will give you like 30 seconds to answer that. Okay, so thank you for answering that first question. So from what I can see, most of you are validating your models using test data. So either from flight, thermal vacuum, or thermal balance test, which is common practice industry. But I can see as well that many of you use some CFD or supplier engineering data as well to validate. And that's something quite as well important. And I can see like as well industry standard internal documents is something quite interesting. So I will cover those aspects in the today's presentation. So now let's look at what methods or approaches do we have to calibrate or validate a thermal model. So we have our simulation model, reference data, test data, high fidelity simulation, or industry standards. We can have like two approaches. The first one is like we follow a manual process. So it means that you modify manually the parameters in your model and you run the model multiple times. And then you check your requirements and you say, okay, my model is validated. I match the test data, I match the industry standard. That's the first method. The second method could be to automate that process. So for that, you can use optimization framework, design of experiment technique, or parametric study to automate that process and remove that manual operations. So then, whatever is the method you are using, you need something that is scalable to validate your thermal model so that you spend less time in front of your, we'll say, computer or workstation or your screen to validate your model, and you can focus on other tasks. The main challenge here is that when you deal with complex model, you might have hundreds of design variable or parameter to adjust, and maybe 50 or 100 sensors. Sensors could be locations in your model where you would like to match your reference data. And the main challenges that you can encounter first when you do that manually is that you need to run the model, let's say 100 times in a manual way. So it means it requires a lot of actions from you, and it can take several months to fully validate a model. Like on average in the industry, to validate a full-scale model, it could be like between 2 or 3 months, for example. So you can say, okay, let's use some optimization approaches to target that challenge. The issue with optimization approaches is that you need more, I would say, involved infrastructure, more on the IT side to run large model in an automated way, maybe an additional tool to automate that workflow. And that basically consumes some of the hardware resources. So in such case, what we have seen in the industry is that we need to reduce the set of design variable parameter to simplify the problem, or to consider few mission profile. So it means that there, even if you do it manually or you automate that, there are some things that you are missing. You cannot perform a complete validation of your thermal model. So another question for you now is like, how do you currently validate your simulation models? What is the process in your company? So I will give you like 30 seconds again. So I can see that most of you have answers. So as we can see here, most of you do that manually, and that's something that we are seeing in the industry because it's difficult to come up with a dedicated tool for that particular activity of validating thermal model. And most of you have internal process that I think you have developed over time. So let's get back to the presentation now. So now I would like to introduce you the adjoint-based approach that we have developed at Maya HTT, which is named TMG Correlation. So TMG Correlation is an add-on to SimCenter 3D Thermal Multiphysics or Space System Thermal, which is thermal solution within the SimCenter portfolio of Siemens. And it combines the TMG Thermal Solver, which is the engine behind the thermal solver, and adjoint-based solver that will speed up and you will see do that validation more efficiently. So what it is? So adjoint-based is because we leverage the adjoint method to compute the gradients. The gradients are the sensitivity of your parameter that we can compute, and we can measure the effect on each parameter on the objective function. So basically the gap between your simulation model and your reference data. So in few steps, we compute the adjoint equation, which is a representation of your model, but in different, we say, numerical fashion. And from there, we can compute the gradient for each parameter, and we can feed then an optimization algorithm with those gradients or sensitivity. So why we are using the adjoint method? So compared to classic gradient computation, for example, that you can get in optimization framework or automated workflow as well, which are usually based on finite differences. If you have n design variable, you need to solve n plus time the system, okay? So this is why when you have large model with a lot of variable, it's not really scalable and you need to reduce the size of your problem. With the adjoint method, we solve one time the model to get data, and then we build the adjoint equation and we compute the gradient. So we actually solve only two systems, and this independently of the number of design variables. So if you have 100 or 1,000, we only solve twice the system. Okay, so and the adjoint method, this is why it's widely used, let's say, in structural optimization, when you would like to optimize a shape and you have a lot of nodes or parts of your model that you want to change over each iteration. Using the adjoint method, you can compute the sensitivity of each node with one solve of the adjoint equation. And it's always used for, let's say, generative design of CFD optimization as well. So that's about the theory of the adjoint part. So now that we have the gradient, we give that to an optimization algorithm, and this algorithm will calibrate the simulation model by minimizing the following function. So you can see here that you have a temperature difference to the power of 2 that is basically it's like a sum of all the targets. So target is a sensor. You can add a weight as well on that, and we sum that for all the times if it's a transient problem. So that objective function is something close to the root mean square error, average over time and over the target, so over the sensors. So, and just to give you a bit of insight, what is a correlation time? So a correlation time is a time at which the model calibration is performed. So it could be a solver time step, it could be a reference data time point, or a time that you specify in the tool, and I will show you that briefly. So if you select all the time, it will gonna be similar to minimizing the area between those two curves that you can see here. So now let's illustrate a bit more what TMG correlation can do on a really concrete case study. So over the last year, we developed with some colleagues very, I would say, for the people familiar with the aircraft industry, simple, I would say, UAV demonstrator, but quite representative, that we derived from existing aircraft configurations. The purpose here was to replace the kerosene-powered engine by hydrogen-powered one, to look at more that technology and as well have the ability to demonstrate some of the boundary conditions and, let's say, validation tool that we can have. So you will see that we have some different components in that model. So we are in SimCenter 3D here. So you can see in the middle of the aircraft, we have the hydrogen tanks in the mid bay. We have some radiation enclosure to calculate the radiation effects. That's basically what I have highlighted here. Several thermal contacts to take into consideration the conduction aspect through the airframe structure. Some temperature constraints to model, for example, the nacelle temperature. And we have as well some convective loads. So convective loads will be used to model, let's say, the air surrounding the avionics. So it could be natural convection, for example. We have some heat loads for each equipment. So the avionics, the equipment in the aft equipment bay, and as well some backup avionics with less power, for example. So in the middle of that aircraft, you can see that we have what we call thermal streams. So those are boundary conditions used to model advection. So here we assume that we have NACA air intake that basically allows some portion of the external air to go inside the bay and cool down the hydrogen tank. And then using those boundary conditions, we can model the flow network and the cooling or heating of the system inside. So that's basically what you have in that model. Here we have the same thing for the aft equipment bay. And that aft equipment bay, the inlet flow is connected to the mid bay in which you have the hydrogen tank. And everything can be done in SimCenter 3D thermal easily. So that's the 3D thermal model that we are going to use today. Last boundary condition is what we call convective zone to model the external environment of the aircraft, and some convective boundary condition for the hydrogen tank to represent the liquid hydrogen inside the cryogenic storage. So that's our 3D model that we're going to use to illustrate the thermal validation. So now let's start with the reference data. So what I did, I generated some reference data which are similar as first flight tests or high fidelity CFD simulation. And those data involve time-varying temperature from 7 sensors located near the avionics, in the nose bay or the aft equipment bay, and around the hydrogen tanks bay as well. So we have 7 sensors, so 7 locations in which we would like to validate this simulation model. So let's see now in TMG correlation how you can import and manipulate the reference data that you might get from your colleagues, for example, from the test engineer. So in SimCenter 3D, you can access TMG correlation from the menu. And then you will see you have one dialog box. So everything will happen in that dialog box. It's a really fully integrated tool in SimCenter 3D. You don't need to open a tool on the side. So how it works, you will select an existing solution of your model, and we will create a new solution, a clone of this one that we will manipulate to perform the calibration or the validation. So then 3 steps to do a TMG correlation analysis: reference data, design variable, optimization. We will start right now with the reference data. We can have 3 types of reference data from a file, CSV file, from name point, which are points already created in the model with a name, for which we will basically import data, so time and temperature data in CSV file that we will basically associate to that point. So then when we'll add that data, we can activate, deactivate that sensor in the tool. We can delete, we can plot as well and get more information. So if we plot, you can check that your data is valid, is good. The sensor maybe work or didn't work during the test campaign. That's something that could happen. So now I'm adding all those additional data and associate to the different name points that I have in the model. You can be even more efficient here if you put together all those CSV files into a singular one, and you can import everything in one shot as well. Second step is to connect your sensor data or reference data to the node or element of your model. It can be done manually by specifying the ID or selecting, or you can use our proximity pairing method that basically use the closest node or element to connect to the sensor. And then when you select one sensor, you can see which node has been paired with him. So now let's compare the simulation model and your reference data. So that's really the correlation step, the first step. So we need to see how far we are from the reference data and if we need to calibrate the model or not. So as you can see, we expose the reference temperature. Original temperature is the simulation model, and we compute the absolute error. What you can do in TMG correlation, you can overlay those 2 data and see how far you are from the reference. So you can use the probing mode here, and you can see that, for example, for some of the sensor here, I'm like between 5 and 6 degrees off. So it requires validation. We need to adjust some parameter to represent nicely the actual behavior. You can as well use the absolute error plot to look at where you need the calibration over time and for all the sensors. So this is fully, as soon as you have imported the reference data, this is fully available to you in the software. So now that I have imported my reference data, that I connected the reference data to my model, I looked into the comparison between my simulation model and my reference data. I'm ready to define the design variable, so which parameter I would like to adjust. So what are my uncertain parameters? So in that model, I decided to play with different heat transfer coefficient and a mass flow parameter. So in the nose avionics bay, we will define as design variable the heat transfer coefficients between the avionics and the nose bay surrounding air, so the air inside the bay. For the hydrogen tanks, it's going to be the same, the transfer coefficient between the airflow, so at the advection portion, and the wall of the hydrogen tanks. For the aft equipment bay, we will use 2 parameters to validate or adjust the model, the transfer coefficient, of course, but as well the portion of mass flow that is entering in the aft equipment bay. As I said earlier, this aft equipment bay receives some airflow from the hydrogen tank bay, and which you can have uncertainty on that portion, and we will gonna use TMG correlation to see how important is that mass flow portion and how it could affect as well the validity of your thermal model. So let's see now how we can create design variable for our uncertain parameter in TMG correlation. So in the design variable page, you have some filtering option to navigate through your model. When you have a large model, you may have like thousands of boundary conditions and thousands of parameters. So you can use some parameter names, source type, and formula to filter and just look and find what you would like to define as design variable. So in that model, I'm going to look for the heat transfer coefficient located on one side of the thermal stream. You can associate design variable for a singular parameter or one design variable for many parameters at a time. So that's what I'm doing here. So one design variable defined as a multiplier for all those heat transfer coefficients. So that's one example that you can do. The second thing that you can do is to look, for example, for the mass flow. So we will create a design variable for the mass flow portion to see and calibrate that parameter. So same thing, you can use the filtering options, which is quite handy actually to navigate through the model and define the design variable. And as well here, best practice, it's always to use meaningful names so that you can retrieve your information quite easily afterwards. So here I just quickly showed how to create two design variables. For the model, you will see that we will manipulate more than that afterwards. So before going into the last step, which is the optimization, I would like to ask you another question around the design variable. So what are the typical uncertain parameter in your simulation model? So if you can answer that, I will give you like 40 seconds. Okay, so let's look at the results together. So what we can see is that most of you have like uncertainty around the conduction, so the contact resistance and conductances. That's that's something with contact between two metal parts that's quite normal. Radiation as well, I see, like the optical properties can play a major role, especially when you have large temperature differences, like for hydrogen topic, so really cryogenic temperature, but for space as well, that's something quite important. And then I can see that the heat generation, material properties, and convection related parameter are as well uncertain for most of you. Okay, so thank you for that. Let's get back to the topic. So now we will define what I call the calibration or validation problem. So our problem today, we will have 7 sensors. So on the, I recap on the avionics and the hydrogen tanks that we will use as targets. We will have 4 design variables to adjust. So 3 parameters on heat transfer coefficient and a last one on the mass flow portion for the aft equipment bay. And we will manipulate 28 correlation times. So I selected different times around that mission profile that you can see here. And so we'll have correlation time for the takeoff climb phase, the cruise, and as well the descent taxi phases. So you have full control on how many correlation time you would like to set up in TMG correlation. You can use singular one, but just keep in mind that the tool will only perform the validation at the correlation time you specify. Okay, so it might affect the accuracy and the output of the tool will be giving. So usually when it's something quite linear with not a big change, few correlation time is enough. But if you have like highly changing temperature, very specific dynamic, and you would like to capture that and calibrate your model for that, you may need to select more correlation times. So it depends on the model and the mission profile you will have to validate too. So then I computed the time average absolute error, which is 4 degrees Kelvin, which can be small for some of you, but when you deal with hydrogen tanks, 1 or 2 degrees Kelvin, for example, can basically be critical for safety, especially for liquid hydrogen and cryogenic storage. So it means that this model requires calibration. So the objective here with the tool, we will try to match the reference data temperature at all sensor locations for the selected times of the mission profile. So how we can define that calibration problem in TMG correlation. So let's get back to SimCenter 3D and TMG correlation user interface. So we have some targets, which are our sensors. You can see that here we can add weight. A weight will be basically to put more emphasis on a specific sensor. So if you have critical components, it's something that could be useful. Then we have to define initial, minimum, and maximum values, so the ranges for the design variables. Here I define very, we say, wide range. But if you know your uncertainty for a parameter, you can restrict that range. It will help the validation problem. Then I have defined the correlation time. So it's a text box. You can manually change that. Another option that is quite useful, especially when you have like a transient problem, is time varying convergence criterion. You can have a specific convergence criterion for the first phase of your mission profile and for the last one. Then number of design cycle, and you can choose one of the optimization algorithm you would like to use. And then you're good to go. So when you click on OK, we trigger the solve. So if you are familiar with Space System Thermal or SimCenter 3D Multiphysics, you can see that we use exactly the same process, same solution monitor. So the first part of the analysis is exactly the same. And here you can see that we start computing the first design cycle. So at that stage, what we do, we build the adjoint equation, we compute the gradient, and then we give that to the selected optimization algorithm that is updating the design variable. So as soon as we reach the end of the design cycle, we do another solve, okay, normal solve of the model, and we compute a new objective function. And we proceed until we reach either the convergence criterion or the maximum number of design cycle. So here you can see 3 types of graphs. You have the design variable history, which is the design variable value. So here those are multiplier, the objective function, history plot through the design cycle, and the design variable gradients. And I will get back to that. Those graphs are quite important to track and to basically post-process the results, okay? So now let's look at the results. So the thermal model without the TMG correlation portion takes 10 minutes to solve the full mission profile. The total calibration time, so it means like the 10 design cycle that I did with TMG correlation, took 2 hours and 30 minutes. Okay, so for like 10 times I run that and solve the adjoint equation, compute the gradients, and get to the last design cycle. The objective function I got at the end was 0.9, so I moved from 4 to 0.9, okay, degree Kelvin, and now the absolute error range across all the sensors is between -8 + 1 Kelvin, okay. In the bottom you have a table. I extracted the initial and final value, and because I defined my reference data, I know which solution I should get, okay. So that's to basically validate and as well see where the tool went. So for the heat transfer coefficient, you can see that whatever is the initial value, the final value after the 10 design cycle is really, really close to the known solution, okay? So it means that I had enough sensors, my problem was well defined so that TMG correlation could converge to the optimal solution. Here, something that we will dive a bit into more is the mass flow portion. So you can see that I got 0.3 as the final value, which is quite far from the known solution. So let's look a bit at why we end up in that value and what tools TMG correlation can give you to assess that result. Okay, so we'll get back to the objective function plot, design variable gradient, and design variable history plot. Okay, so what you can see here is that since the design cycle number 4, so after 4 iterations, we were almost converged in terms of results. Okay, so like more or less we reach a plateau for the objective function, and that's basically is coincident with the behavior of those two design variables. So those two design variables, the mass flow portion and the heat transfer coefficient for the aft equipment bay avionics, they impact the sensors that we are in the aft equipment bay. And you can see, especially for the mass flow portion, that the gradient, so the sensitivity of the objective function or the gap between your reference data and your simulation model, this function is not too sensitive to the mass flow portion. So what it means that for that problem, the way I define it, the reference data, the sensors I add, changing that mass flow portion does not affect a lot the gap between the reference data and your simulation model compared to the transfer coefficient. So this is why you can end up with a value that is not the right one, but you end up with the right thermal results, okay? Because at the end, the tool solves a mathematical problem. Okay, so here, if you would like to achieve the best value, maybe we need to restrict the range, okay, of that parameter. Usually mass flow portion in an aircraft bay, you can know that because you know a bit like the valve, how the flow is going in, the pressure differences. So that's something you can control a bit more. And at the same time, you can see that the sensitivity here or the gradient is quite useful to give you that information. So now I have results. So let's look at how we post-process results in TMG correlation user interface. Okay, so as soon as it's ended, you open TMG correlation. We can do the same type of plots than before. Okay, so for that, we need to load the original solution results and the correlated simulation results. So this is what you are seeing right now. So the first plot I'm going to do is the temperature plot for the hydrogen tank sensor. So you can see that we moved from the dashed line to the plane line, and we are now right onto the reference data. You can see that for some location, we are moving a bit away. So it means that maybe the correlation times that I have selected, they are not, I don't have enough correlation time for those sensors. I might need to add a bit more. So that's one takeaway, for example, from that graph. If we look at the avionics sensor, you can see that from the dash line to the plane line, I completely close the gap in 10 design cycle. And that shows pretty well what we have seen with the design variable value, that I got the heat transfer coefficient value that I was expecting, okay, the known solution. So that's really quite good results here. Now let's look a bit more at the convergence and the design variable value. So what I have shown in the slide previously. So you have the same information here in the user interface. And that's something you have, and you have as well in other files that we write in your run directory. So if you are satisfied with the results, the last step is to update your model. So what we do is we ask the user to create or select a folder in which we will copy, update, and save a new and clean simulation file with the updated parameter. And that's something that is done automatically for you. You don't need to copy and paste the value in a new simulation file. That's done right now automatically. So you see a summary here in the information window of all the original formula, updated formula. So you have like the history of the what TMG correlation did for you for all the design variable. So that's a summary of the update, okay, with the path where the model are located. And we already open the new sim file for you in the background. So you can see here that now you have one solution that is correlated, saved in a new sim file. And for example, here what I'm going to do, I'm going to show you what we did in the boundary condition. So let's open one of the thermal stream in which, for example, we modify the mass flow portion. So what we do with TMG correlation, we replace the first value of the parameter by an expression that contains the multiplier and the original content of the boundary condition. So in your model, you always have a trace of what was there before. So we kind of keep the history and the original setup of the model. Okay, and you still have access to the previous model as well with the correlation setup. So you can do multiple correlation on the same model and generate multiple validated model if you want. So last question on that demonstrator that I have for you. What I would like to ask is, how much time do you spend validating your simulation model? So is it like in the order of magnitude of a week, a month, or more than a month? So I give you a bit of time. Okay, so let's look at the results. So from what I can see, most of you spend around a month maximum, we say, to validate your model. So that's a task that consumes a lot of time, and that's something you would be able to speed up with TMG correlation, for example. So now we are at the end of our talk today. So in summary, so first conclusion is that the shift left approach, or we say trend of performing simulation earlier than before, require validating thermal model earlier and faster than before, of course. Otherwise, we're going to add more task to the thermal engineer, and that's something we don't want. So if we want an efficient design process, we need a dedicated tool to perform model validation and calibration. Otherwise, for example, you will spend even more than a month to validate all the thermal models. And so what I presented today is how TMG correlation and its adjoint-based approach, so the ability of solving and getting the sensitivity for a lot of design variable in a cost that is quite small for the for industrial model. So that tool can allow you to validate complex thermal models. So currently, the model I show you today is representative, but we can support even more complex thermal model than that. And that tool can speed up the validation procedure with high accuracy, as you could see. I could retrieve the value I knew, and that tool as well automate that. Okay, so you don't necessarily need to sit in front of your computer while it's iterating for you. So, and to conclude, so just a callback from the first question I asked you. So if you start to be smarter for validating your thermal model, I hope that is going to help and will stop watering or cooling the aircraft and start doing more simulation. So, and that would be possible if you start using TMG correlation. So last question for you before the Q&A session. Okay, so thank you for that. We will go now in the Q&A session. So I'm looking into the question right now. So I have a first question. So would this TMG correlation method work well for a large number of variables, more than 100? So what sorry, just going there. What I can say with a customer, so unfortunately I cannot share that. I supported them with a case study. They wanted to validate a model that involved more than 223 design variables, so very large model with 70 sensors. So the TMG correlation can work with that. It computes, it goes until the end. The complexity is more on the post-processing side because you have a lot of data to manipulate, a lot of sensitivities from the parameter to look at, but it can do it. It can help you actually to narrow down, for example, from 200 design variable to like the most important one, let's say 100. And that's more or less what we did with that customer. So yeah, it can work with very large number of design variable. So I have another question. So will this tool be adapted to correlate structural models in the future? So actually not. So TMG correlation is really tied to the TMG thermal solver in SimCenter 3D. So if you are looking for a tool to correlate structural model, that's not the right tool to look at, but that's the same, I would say, approach can be used for structural model. So that's something that we can look at. So I have another question. What's the relation between number of simulations and number of design variables? So there is no relation, as I said. With the adjoint method, whatever is the number of design variable, we solve one time the model, we construct the adjoint equation, and we solve the adjoint equation to get the sensitivity for all design variable in one shot. So whatever, if you have 2 design variable or 100, we only do those 2 steps. Maybe behind that, you might ask what is the cost. So if you have more design variable, of course, in terms of numerical manipulation, we need to compute more gradients, but you don't have this n+1 cost that you may have with finite differences classic approach. So the cost is kind of independent between number of simulation and number of design variable. So I'm looking into the question. So you have a question. So is it mandatory to have simulation objects, thermal constraints, or other boundary conditions created with existing parameters, or raw number can be used as design variable for the first iteration? So if I have well understood that do we need like existing boundary condition, or if we can create on the fly? So you need a model that has already thermal results to start TMG correlation, so boundary condition defined. And then you can either define a multiplier that basically will multiply the content of the parameter you selected, or we have another method that's basically called substitution. So we substitute the content of your boundary condition. So let's say the transfer coefficient, instead of multiplying it, I will remove what you have in your boundary condition, let's say convection to environment, for example, and we will put a new design variable. And this can be used for for TMG correlation. So I hope I have well answered that. And we support as well expressions. So if you have expressions in your space system thermal model or multiphysics model, you can use the expression as a design variable as well. So you have a question, can you show how is the data structure in your CSV file? Yeah, I might have an example right now. So we do have a template in our online help as well that you can look and download. So here, this is a CSV file that you can use directly and import for your reference data. So what you need for it's comma separated file. Huh? You have the name of your sensor separated by comma, then you have XYZ coordinates, so in the Cartesian system, okay, and then time temperature data, okay. So this is what when I say reference data file, the CSV that you can import, you import that directly, and we will create 5 sensors automatically for you. So that's the template, and there is one given with the online app or the 2 tutorials that are accessible actually for TMG correlation. So that's the format. So any other question? So you have another question. Is it necessary to have data saved in uniform time interval? No. So as I said during the presentation, TMG correlation, you specify the correlation time. So let's say you have solver time step, time points from your reference data, not like a uniform time interval. Then you can define and say, I would like to have a correlation time in between. Okay, so that's possible. So what we're going to do, we're going to perform some interpolation between your reference data and the correlation time, and we will compute the error at that time you have requested. So we can do that. It's not a problem. The only thing that you must be careful with is that if you have a highly nonlinear temperature profile and you select a correlation time quite far from your reference data, maybe with the interpolation that we're going to do, we're going to basically compute an error that is not really accurate. Okay, so that's something worth looking at when you specify your correlation time. By default, in the TMG correlation user interface, we populate the correlation times with the solver time step plus the test data time points or the reference data time points, so that you have only correlation times that are really good, but you can still modify that list and remove and add more. That's up to the user. So do we have other question? So I have a question here. Do we have real industrial cases of TMG correlation usage that you can share? So I have something for space that I can show you right now. Sorry. So it's two slides of like a space company named Satellogic. They did use TMG correlation at the same time that we released the tool almost three years from now, actually. So Satellogic is a space company located in Argentina. They developed imagery satellites. And so they did 2 things for us. They did like beta tester just before the release to the market, and then they continued using the tool as well. So those are results they presented at a conference back then. So on the top right side, you have their satellite and digital twin or simulation model they use for that evaluation of the tool. So what they did, so you can see on the right side, they compare basically their manual approach of correlating that model and the results and the time as well, compared to using TMG correlation. Okay, so for example, using TMG correlation, they moved from 2 to 10 degrees off with the test data. So it was in-orbit data, so actual test data located at a bit more than 20 sensors location. And using TMG correlation, they moved all the sensors below 3 degrees of temperature difference with the test data. The overall work with that model, which is a model that runs really fast, they moved basically from 3 months doing that manually and that iterative process to 1 week. So fully automated, a model that runs fast. This is really where TMG correlation is useful. And one correlation analysis took 10 minutes. And they got, as you can see, more accurate results than what they did manually. So that's an industrial use case that I can share. I had others, but unfortunately for IP reason, I cannot share, but that's one of the nice story that I can share with you today. So last question, we are at the top of the hour. So last question, it's a more comment. I see in your example that you have an absolute error of 8 degrees Celsius at one time step. Is that a problem? So if you have an error, like a larger error at one time step, it means that, for example, around that time, you might need to define a correlation time. Okay, so for that example, I selected a few times, not all of them. But for transient, because we perform the calibration at specific time, if you want the highest accuracy across the entire mission profile, you should keep all the correlation time, or maybe to add more. I have some customer in some specific industry, they are really highly nonlinear models and very long transient. They need to add correlation time to make sure that they capture properly the thermal behavior, so that even outside the calibration, the correlation times, the model is still good and accurate. So that's something I can say about that example. So 2 minutes left. Any other question from the audience? So I have one here, maybe I missed it earlier. Can you correlate 2 or more cases simultaneously? So it means hot and cold cases, for example. So TMG correlation works with one solution. So when you correlate, let's say, hot case, and then you can validate that on the hot case. So simultaneously you can't, because you are already tied to the energy equation, so the matrices of your model. But if you want to basically automate that, that's something I have seen on customer site, is that you can do the correlation for the hot case, and then you just put that in a parametric loop, and then you do another correlation on the cold case, and they use both results to calibrate the model. So that's something you can do kind of more as a post-processing than inside the tool, actually. But that's something I already have seen in application. So I think I went through all the questions. So if you have any other questions, you have my contact here. Feel free to reach out to us, to read the white paper, to go on the website. And so thank you for attending. I wish you a great end of the day, or great afternoon, depending on your time zone. And I'm looking forward to discuss with you about TeamG correlation in the near future.